Hi everyone, I'm Luz García, a postdoc fellow at Universidad EMCEE, and I want to talk about how to study early energy models from different approaches. I want to start by thanking the organizers of Cosmology from Home for giving me the opportunity to talk about this research I've been doing for the past few years. So to introduce this topic and give you some motivation on why to study early dark energy models, it's important to remind everyone that in 1998, these three people discovered that the universe was expanding, but not only that this expansion was actually accelerated. And we can explain this with different approaches, but I'm gonna focus in particular in the possibility that this expansion is due to the something that we call dark energy. And to be absolutely upfront with this, we have no idea what's the nature of this dark energy. That's just a name to describe that we don't really understand what's going on with the space-time. The other possibility, if there is not something like a dark matter energy component, is that the universe itself is expanding due to a variation in the geometry part of the field equations. But that's something I'm not going to consider. In the lambda CDM model, this dark energy is supposed to be described with something that we call cosmological constant, and that is described with this lambda term in the equations down there. And this was one of the things that lead the Science magazine to mention that this discovery that the universe was expanding in accelerating fashion was actually the discovery of the year in 1998. In 1999, Michael Turner, that we're seeing there, assumed that this component that we haven't detected yet was due to the fluctuations of the vacuum fields. And that was supposed to be the nature of the cosmological constant, but there are huge discrepancies in the orders of magnitude of these two terms from high energy physics and from the cosmological side. That's why I'm going to consider that there should be something else that is causing this accelerated expansion. And if it's not the cosmological constant, should be something that has to be evolving during the expansion and the history of the universe, and that had to be subdominant during the radiation and matter domination epochs in order to don't break the different processes that we have already detected and measured. So according to our cosmological model, there should be something about 68% of dark energy, something about 5% of all the matter, the visible matter that is composed by atoms, and then something like 25%, 27% of dark matter. But that's something that I'm going to skip for now. The other issue that we're seeing at this point is that the values, different values of the Hubble parameter, the Hubble constant, are varying according to the method that we're using to measure it. So if we use measurements of the early universe, like Planck or DES, we find that the value, it's something about 67 kilometers per second per megaparsec. But if we use the present day universe measurements, this value is way larger. And this difference or tension has been called as the Hubble tension. There is not a reason why the values should be that different, and they are actually at the same level of the error that we're getting in these measurements. So it could be something due to the way we're measuring, or is there something fundamental that is causing this discrepancy? In order to study this issue, we're going to use Cosmology version 1.6. And basically what Cosmology does is that it estimates the cosmological parameters to pre-existing, using different observables and mapping out experimental likelihoods in the different techniques of our models. And to explain that, I'm going to calculate that, I'm going to use the sampler EMCEE that basically use walkers in order to cover all the parameter space and explore the different possibilities for the parameter values. And then each walker is going to move to a different place randomly once it reaches a particular threshold that has been predefined. So I'm showing in the left the different parameters that are included in the sampler, and on the right I'm showing what's the basic methodology that the sampler uses in Cosmology. In particular, I'm going to use these parameters, these values for the parameters, and I'm using a minimum acceptance fraction of 0.25, which means that it's above the minimum that has been imposed in the code. So I'm going to explore different parameterizations in Cosmology in order to find out how well it performs. The first model, I'm going to try the CPL, the Chevalier and Polarski and Linder model that accounts for a linear parameterization that evolves with the scale factor. And this stated question has been explored in different works. So I'm just showing what we get when we use different observables in Cosmology. The second model, that is a toy model, it's a quadratic dependence with the scale factor in the equation of a state. Clearly, this is not physically motivated, but it was a good way to test the results that we were getting with Cosmology. And as you can see here, the model shows some predictions for the omega b parameter as a function of the Hubble parameter little h. The third method, that it's something that has been already been published, it's a parameterization we proposed in 2021 that basically assumes that there should be two different points where the dark energy model is going to be present. It's going to be non-negligible during radiation domination epoch, and then it's going to move to be more predominant during the de Sitter era. And in order to make that transition, we're going to use these values of M, which is a parameter, a free parameter of our model, which is going to allow us to have a smooth transition from radiation to the de Sitter domination epoch. Those are the results that we published at that point. And for that, we used a pipeline that is described in this work. However, okay, and here we are also showing how the dark matter, the dark energy density fraction evolves as a function of redshift with the best parameters we find there. And also what's the evolution of the equation of the state as a function of redshift. And we're also comparing with the magenta line, which is the prediction for the lambda CD model, where omega is assumed to be constant and has a value of -1. One important takeaway message here is that the time of or the age of the universe is actually shorter compared with the predictions from the standard cosmological model. We repeat this procedure, but this time we're gonna use cosmosis. And as you can see here, we assume the same parameterization, but this time we're also assuming the different observables that I described in the two previous models, and those are the results that we get. So we have a prediction for H naught, omega m, and therefore a prediction for omega phi, which is the value of the dark energy density today. Finally, we're exploring an additional model, a modified Chaplin gas, which is assumed to be due to the existence of non-linear electrodynamics during radiation, and it actually leads to a parameterization that is quite similar to the previous one I showed in the previous slides, and that was explored and described in Garcia in 2021. The interesting thing here is that the motivation is completely different, because this Chaplin gas, it's also able to explain contributions of dark matter. Finally, I want to finish by telling you that we are also using some CFD code with OpenFOAM in order to describe the effects of dark energy with this code, this method that is based on the computational fluid dynamics codes, and in particular OpenFOAM, that is an open source code. If you want to hear more details, we can talk about this during the session of questions. And I want to close by mentioning that the current Hubble tension could be addressed by introducing these dark energy models, have some dynamics during the different epochs of the universe. These models predict the faster evolution of the structure because they departure earlier from the radiation domination epoch compared with lambda CDM. And we're gonna carry on studying these early dark energy models, and in particular, the ones that I described at the end. We're also studying different cosmological likelihoods in cosmosis, and we're going to explore also different estimators and samplers in order to have better constraints on the parameterizations. And finally, all of these results will be soon tested by Euclid, the Nancy Green-Stroman Observatory, or WFIRST, the Bernard Rubin Observatory, or LSST, and in some degree by James Webb. Thank you so much, and I hope you have questions and comments and that we can discuss later in the conference.